we'll continue from where we stopped last week. We were discussing about the energy from chemicals, energetics, exothermic, endothermic reactions. We're discussing about the energy profile diagrams and the application, mainly the application of Q equals MC theta equation, and also delta H equals minus MC delta T. The situations you have to consider when handling these two equations. Definitions of various enthalpy terms: enthalpy of atomization, combustion, neutralization, enthalpy of solution, likewise. And I mainly explain the difference between the enthalpy of dissociation and atomization, and also various experiments to find these enthalpy changes. And then I give introduction how these enthalpy changes are found with respect to bond enthalpies, with respect to energy required to break the bonds, energy release when the bonds are made. In fact, I explained what is endothermic, exothermic reaction in terms of these bond energies. In exothermic reaction, the energy released when the bonds are made is more than the energy absorbed when the bonds are broken, because any chemical reaction involves bond breaking and bond making. To break the bonds, you have to supply energy. When the bonds are made, energy is released. So if the energy released when the bonds are made, if it is greater than the energy absorbed when the bonds are broken, such reaction is said to be exothermic. Likewise, energy absorbed to break the bonds, if it's more than the energy released when the bonds are made, such reaction is said to be exothermic. Then I define the bond energies. Remember, the definition of bond energies is important that you define in gaseous state. Bond energy is energy required or energy released when 1 mole of gaseous atoms, energy required to break 1 mole of bonds, or energy released when 1 mole of a bond is formed in gaseous state. Bond energy is always defined in gaseous state, not in any other state, because if it's solid, then part of energy is required for melting, and the part of energy is required for evaporation. So you need to count only from gas to atomization. As for bond dissociation energy, that is energy required to break 1 mole of bonds in gaseous state. So that's the difference between bond energy and bond dissociation energy. And I discuss about enthalpy of dissociation. That's the energy released or energy required, to when 1 mole of substance is broken into its free gaseous atoms, right? Anyone remember where I exactly stopped? I remember explaining about these bond energies. Did I do question 28? Limitations in calculating the enthalpy change using mean bond energy. 27. Did I explain 27 and 28? On question 26, okay. Right, so enthalpy dissociation is the energy required to break 1 mole of gaseous, 1 mole of substances, free gaseous atoms. This is what exactly happens in dissociation. It is same process as atomization, but when you define atomization, that is the energy required when 1 mole of gaseous atoms are formed from its constituent elements in the gaseous state or in the standard state. Right, so this is the difference. So here in the atomization, it is 1 mole of gaseous atoms you're forming. That means you're forming 1 mole of gaseous atoms from its constituent elements under standard conditions. This is what I've written above is the atomization, enthalpy atomization of chlorine. And what I've written below is the enthalpy dissociation of chlorine. In both situations, you're breaking bonds, but in dissociation, you're breaking 1 mole of substance to form free gaseous atoms, and in atomization, we are forming 1 mole of gaseous atoms from its constituent elements under standard conditions. So if you take sodium, right, the gaseous sodium to solid sodium, this is, solid sodium to gaseous sodium, this is atomization. right, from its constituent elements to form 1 mole of gaseous atom. So in dissociation, we are breaking 1 mole of substance. That's the main difference between the dissociation and atomization. So the energy required to break 4 carbon hydrogen bonds is given as plus 1664 kilojoules for mole energy, which means this is the enthalpy of dissociation, which is given. That means to break all 4 bonds, 1 mole of methane. The question is, calculate the energy required to break 1 CH bond. So then simply, this is for breaking 4 bonds. So 1 bond you divide by 4, right? This is the energy required to break 1 more bond, 1 CH bond, which is 1/4 of it. Now, when you're breaking these CH4 bonds, right, look what actually happens. You have carbon, which is +6 nuclear charge. Hydrogen is +1. Let's have 4 hydrogens here. So if you analyze the dot and cross diagram, the bonding, you have like this. 4 hydrogens around the carbon. All hydrogens are +1. So if you break 1, now each bonding pair is attracted to this +6. So what happens if you break 1 of the CH bonds? If I break this bond, then this +6 charge is concentrated among only 3 lone pairs, which means approximately 1 lone pair is attracted by +2 charge. If I further break another CH bond, then this +6 is attracted now by only 2 electron pairs. Right, so now the effective nuclear attraction is much greater. Right? If I break this CH bond, the attraction is even more, and the last CH bond is the most difficult to break. The attraction is the most highest. So therefore, we understand to break each and every CH bond, you need a different amount of energy. For example, you have the first CH bond, you might need about plus 180 kilojoules. Second CH bond, you might need about plus 275. The third CH bond, you might need about plus 400. And the last CH bond, you might need about plus 800, for example. So each CH bond to break, different amount of energy is required. So if you add all these 4 bond energies separately, you'll get this total, which is 1664, right? So when I divided this by 4, I get the energy required to break 1 CH bond, which is 416, but you cannot see the 416 anywhere in this, right? None of the values are 416 actually. So this 416 is basically the average bond dissociation energy. It's not the true bond energy. It's the average out of all, right? Average out of all. Clear? So the specific bond enthalpies for each CH bond differs in methane. What do we call the above value, which we got for the dissociation of 1 CH bond? You can write the answer as average bond dissociation energy. Average bond dissociation energy. So last week we discussed about how to find the enthalpy change in terms of with the help of the equation Q equals mc theta, or delta H equals minus mc delta T. So today I'm going to concentrate on how to find the enthalpy changes using bond enthalpies. Now, when you're doing this, all what you do is, first of all, calculate the energy required to break all the bonds, which is endothermic. Bond breaking, energy required to break all the bonds you calculate. Likewise, you calculate energy release when the bonds are made, which is negative, exothermic. In order to find the enthalpy change with the reaction, you simply add these two values, add the values with the sign, you get the enthalpy change value. You add these two values with their respective signs, the plus and minus sign, you get the delta H, the enthalpy change. Right? So if the energy release when the bonds are made, the minus Y, if it is greater, then overall reaction becomes negative, exothermic. If the energy required to break the bonds, plus value, if it is greater, the overall reaction becomes endothermic. Right? This is how, when you know the average bond dissociation energies, you can add them and find the enthalpy change. Right? So there are some limitations in this calculation because what you get here is the experimental enthalpy change, not the actual enthalpy change of a reaction. Because the reason, there are some limitations in this calculation. The limitations are that mainly the bond energies which we use, they are not the actual bond energies. They're almost close to the actual value, but the average bond dissociation energy. So that's one of the limitations in this type of calculation, right? So, and also the bond enthalpies, the average bond enthalpies, they are measured under the gaseous state, right? I defined the bond energy, if you remember, energy required to break or make 1 mole of bonds in gaseous state. In gaseous state. But the equation, we don't handle all reactions in gaseous state. Sometimes if water is produced, for example, it's not in gaseous state at room temperature. It's under standard conditions. It's liquid. Sometimes you have carbon dioxide gas, oxygen gas in the equation. The standard state is, of course, that is gas. Then fine. But sometimes you have solids. So bond energies, when it comes to those, will actually differ because we know the bond energies which is calculated from the gaseous state, not from solid or from liquid state, right? So there are two main limitations of this type of calculation of enthalpy change. The bond energy is measured on the gaseous state, but the reactants and products of a reaction may not always be in gaseous under standard conditions. Sometimes standard conditions can be liquid. Some standard conditions will be solids, right? And the mean bond enthalpies does not correspond to the actual bond enthalpies, the limitations of this calculation. So you can write the answer for the 27th one. Calculate the energy required to break the bonds. Calculate the energy required write the answer for this 27th. Can you hear me? Calculate the energy required to break the bonds of all the reactants. Likewise, calculate the energy released when the bonds are made at the products. Calculate the energy released when the bonds are made at the products. Write in brackets, which is exothermic, negative. The enthalpy change can be found The enthalpy change of reaction can be found by simply adding these two enthalpy values with their appropriate signs. Which means plus or minus sign. In these enthalpy values with their appropriate sign. It means plus or minus sign, because reactants negative, reactants positive. Reactants, you always break, you give energy. The products negative. So we add these two values with the signs. If the negative value is more than the positive value, it becomes exothermic. If the positive value is more than the negative value, the reaction will become endothermic. Right. So let's see how the calculation is done. We'll start with this basic one. The reaction between methane and chlorine is represented by the equation. This is average bond dissociation energy. That means all the values are measured in gaseous state. Let me, first of all, when you come across a question like this, the best thing you can do first is to draw this plate formula. You know why I'm saying that? Because you know exactly to identify the types of bonds which are broken and the number of bonds which are broken and formed, right? This plate formula is easy for us to identify. Now, you can see in this reaction, and there are two ways to do this. One is that you break all the bonds at the reactants. When I say all the bonds, that means you're breaking 4 CH bonds and 1 CC bond, CL-CL bond, breaking all the bonds at the reactants. And then you calculate the energy release when all the bonds are made. When I say all the bonds, you are making 3 CH bonds, 1 CC-Cl bond, and 1 HCl bond. All these values will be positive. All these values will be negative. In order to find the enthalpy change, say this is X and that is Y. To find the enthalpy change, you add the X and the Y values, right? You add the X and the Y value. If the Y, the negative value, if it is more than the positive, the reaction becomes exo. The positive value is more than the negative, reaction becomes endothermic, endo, right? This is one method. The other method is you don't break all the bonds, right? That's the first method. You break everything and you make everything. Second method is you break only the relevant bonds which are actually broken. You can see here, you only break CH and the CC. Only the CH and the CL-Cl. That's only actually broken. And then you're making actually CCl and HCl. So that way, it's easy to do the calculation. It's less calculation, right? You get the same answer, right? You break only the relevant bonds which are broken. You identify from the displayed formula which bond is actually broken, right? And which bond is actually made. So you only do the calculation for those.